We are now in section 6.6, and this will be the last section we cover in chapter 6. Sections 6, 7, and 6, 8 are optional. All right, so a common task in science and engineering is to analyze and understand relationships among several quantities that vary. This section describes a variety of situations in which data are used to build or verify a formula that predicts the value of one variable as a function of other variables. In each case, the problem will amount to solving a least squares problem. So what you learned in section 6.5, least squares problems, that knowledge is going to be used for these applications. Okay. They comment, hold on here. Okay, so for easy application of discussion to real problems that you may encounter later in your career, we choose notation that's commonly used in the statistical analysis of scientific and engineering data. So instead of the matrix equation A times X equals B, we're going to write the matrix X, big matrix X times vector beta. That's Greek symbol beta. So hold on, let me just, let me see if I can highlight it here. Yeah, the matrix X, that contains your design, that's called your design matrix, times the vector B, which is your parameter vector, will equal the vector Y, which is the observation vector in the model. Okay, now let's start off with a very simple example here. A line of best fit, least squares lines, or a line of best fit. How many have seen regression lines? Or you have data. You have data. That has coordinates in the XY plane, and you have a scatter plot, and you try to draw a line of best fit through the scatter plot. Mikhail's seen that. Who else has seen that? The line of best fit. Good. Marcella has. Yes. And the concept is all that what you learned. I mean, in that I want to say this the right way. We can relate those ideas to linear algebra. So let me show you here. Let me go down here, and we look at figure 1, and what you have here is you have some data points. Okay, you have some data points, and then you have a line that goes through the data points. Okay, Y equals beta naught plus beta 1 times X. Now, does that line of best fit, so to speak, I want to say it the right way. I mean, what we're trying to say is we observe for a group of individuals, we observe like a dependent variable X. I want to say this the right way. So like, let's say that you wanted to predict a person's height. Okay. Or let's see. Yeah, let's keep it simple. So if you wanted to predict a person's height, could you possibly look at their foot size? Do you think a person's foot size is somehow related to a person's height? In other words, people with larger feet tend to be taller. So what I'm trying to say, let me go to the whiteboard. Let me be more, I want to make sure we're all comfortable here. Yeah, well, that's right, Mikhail. And so you see, you can have data, you can collect data on individuals. X is the foot, maybe the foot length, and Y is the height. So, for instance, you can have a person who is has a foot length of 8 inches, okay, and let's see, their height maybe is 60 inches. You can have a person that has a foot length of 6 inches, okay, and one moment here. And maybe they're 45 inches tall. Okay. You could have a person that is, I want to be careful how I phrase this. You could have a person that has a foot that's 12 inches long. Right. Well, you know. And let's see here. One moment. And well, that would be kind of, maybe they are 72 inches or 6 feet tall. The point is you collect the data. You collect the data and you get information. So see, what you can do is you want to incorporate, I want to say this the right way. I want to say it simply. The idea is that does foot length predict height? Well, I think you would agree that on average, if a person's foot is longer, they're probably going to be taller, but it's not like a one-to-one thing. In other words, it's not like 100% sure, right? So you have variability for different foot lengths. People have different heights, and in general, the longer the foot, the taller the person is. But it's not like everything's in perfect proportion. So what happens is if we go back to the thing here in the picture, you plot these coordinates, these XY coordinates, which would be foot height and the height of a person, foot length and height of a person. But not all the points don't all, and actually I guess in this case the line's going down, so our line of best fit would have to be going up, right? But in this case they have it where in general, as your predictor variable X increases, the observed variable Y decreases. Okay, but the point is that the data do not all fall on that straight line. Okay, so if we wanted to find B sub 0, beta sub 0, and beta sub 1, we could not find that. We could not solve that. Or another way of thinking about it is if you consider, okay, if you consider that a predicted value based on the model says you can predict an observed value y by taking some value beta 0 plus beta 1 times x. And it should be true all the time. But it's not true all the time. It's not true all the time. You have all these equations here, okay, but this beta 0 and beta 1, there's no solution for those values, for those variables. There's no solution because in the picture here, the coordinates do not fall all on that straight line. So this turns out to be a least squares problem. And what we want to do is make the distance between the least squares, we want a line of best fit, a line that minimizes the distance between the observed values and the predicted values based on the model. And all of this can be expressed in terms of a least squares problem. All of it can be expressed in terms of a least squares problem. So if you have a design matrix X there, the design matrix X, notice the first column is all ones. And that's because of the beta. So let me just show you this here. Let me just show you this here. So, okay. So, okay, beta naught plus beta 1 x1 equals y1. Beta naught plus beta 1 x2 equals y2. Let's do 3. And beta naught plus beta 1 x3 equals y3. Okay. This is a system of equations. We have 3 equations in 2 unknowns, right? The beta naught and the beta 1. Those are our variables we want to solve for. We are given the values of x and we're given the observed values of y. Well, the data we have our x values and our y values. Now we want to solve for beta naught and beta 1. Okay, if we were to rewrite this system in matrix form, okay, we'd have 1, 1, 1, x1, x2, x3. Okay, times beta naught, beta 1, that vector, equals y1, y2, and y3. This is your design matrix X. This is your parameter vector B. And this is your observed vector Y. So this is your, hold on here. I mean, I have it right. This is your observation vector. This is your design matrix X. And this is your parameter vector. Okay. Are we okay? Are we okay going from, this would be if we had 3 data points. Are we okay going from here, the system of equations, to the matrix equation? Give me a thumbs up if you're okay with that. Good. Good, Belen. Good, Mikhail. Good, Marcella. Excellent. And notice we have 3 rows by 2 columns times a 2 by 1. That's going to be a 3 by 1. Okay, now what's the issue? What's the problem when you, I mean, I'm not saying it's always a problem, but what is generally the problem? Like, let me say it the right way. Like if we had just equations 1 and 2, could we normally solve for our variables b0 and b1? You know, 2 equations and 2 unknowns. Could we normally solve for our variables? If you have two, so what I'm trying to say is this, like here's an analogy. Like if you have, you know, x minus 3y equals 4 and 2x plus 5y equals 6. Think back into algebra 2. Could you normally solve that system of equations? X minus 3y equals 4 and 2x plus 5y equals 6. Yeah, and why is that? Because you have 2 equations and 2 unknowns. That's right, Cameron. 2 equations, 2 unknowns. We can usually find a solution, unless the 2 equations are, unless you have like an inconsistent system. But here, we don't have 2 equations and 2 unknowns. We have 3 equations and 3 unknowns. And so unless one of those equations is the same as one of the other equations, we're not going to be able to uniquely solve for those B0 and B1. That's equivalent to if you have a line of best fit, you know, you have 3 data points here. You have 3 data points. Okay, so you know you have x1, y1, x2, y2, and sure, x2, y2, sure. A line, and remember, in this situation, our model, right, is beta 0 plus beta 1 x equals y. That's the model we're using for this data. If I have just 2 points, I can draw a line through those 2 points and figure out what beta 0 and beta 1 are. But when you add a third data point on there, okay, a third data point, x3, y3, you're not going to be able to find a line. You're not going to be able to have a line that passes through those 3 points. So you can't uniquely solve. You can't solve for beta 0, beta 1. All you can do is find the least squares line, the line of best fit, and that least squares line requires you to find least squares solution. So let's go ahead and look at example 1 here in the book. Does this make good sense? Does this make, before I go back there, does this make good sense what I'm talking about here? All right, very good, Cameron, very good. Okay, so let's go to this example here in the book, first example. Here, in this example, They want you to find the equation of the least squares line that best fits the data points. So here is the design matrix and the observation vector. Notice that the 4 coordinates there in example 1, the y values are 1, 2, 3, and 3. So that forms your observation vector. Now all you want to do is use the normal equations. Well, the normal equations with the new notation are given here. And so you solve the normal equations for B, and it turns out that the X transpose X here, this is invertible, and so the vector B, well, let me go back here. Let me go back to the whiteboard. Let me show you here what they're getting at here, what they mean. So in section 6.5, okay, the section 6.5, the normal equations, well, the normal equations okay, we're simply hold on, I have it here. Yeah, A transpose times A times X equals A transpose times B. Those were the normal equations. In section 6.6, and by the way, the system that you were trying to solve in section 6.5 was A times X equals B. The system that you're trying to solve in section 6.6 is design matrix X times parameter vector B equals observation vector Y. And so the normal equations are going to be X transpose X times something equals something times something. Can you tell me what's going to go here? X transpose X times, what vector is going to go there? That's right, Mikhail, vector beta, Greek symbol beta, equals, okay. Let me just try to have it, I want to have it looking good. Okay, that's going to equal what's going to go here. What goes there? So compare AX equals B with XB equals Y. And then compare the normal equations for AX equals B with what the normal equations have to be for X times B equals Y. What has to go here in this spot? You know, come on, you know. Somebody tell me. All right, Mikhail, go ahead. Go ahead. I want us to move along here. I understand. I understand you. Yeah, that's fine. So I think, I mean, X transpose. I completely understand that. And then here we have what here? The vector y. So if X transpose X, thank you, Mikhail. If X transpose X is invertible, all right, very good, then the least square solution beta hat is going to equal X transpose X inverse times X transpose B. So that's analogous to A transpose A inverse times A transpose B. That comes from theorem 14 in section 6.5. And in general, we hope that X transpose X is invertible, because we don't want our design matrix to have linearly dependent columns. One moment. Hey, Alan, let me call you back a little later, okay? I'm just teaching the students, okay? All right, thanks, Alan. Okay. So, like for instance, if so, for X transpose X to be invertible, this means that X is linearly independent. Now let's suppose that you had a design matrix where let's say this were your design matrix, 1 1, and let's say that 3 3 is your second column. Okay, so 1 1. Hold on. One moment. Right. So let's say that you sample. I want to say this the right way. Okay, let's say that you sample 2 people. Okay, and I have to think. All right, I'm gonna show you here, but may I? Is everybody good here? I'm gonna have to get a clean space here to show you this. All right, it's in the recording. Okay, let's go back to that example where we have. Was that supposed to be a Y on the previous page? You mean what I typed? Hold on. So hold on. Bottom right. All right, and I can't go back to the previous page. Let me just write it here. So section 6.5, you have, hold on. I want to make sure everything's good here. So 6.5, if A is linearly, no, I'm not saying this right. Are linearly independent, then Okay, then, see, I have to go back to the book here. Right. Then for the system A times X equals B, X hat is equal to A transpose A inverse times A transpose B. That's section 6.5. In section 6.6, if the columns of the design matrix X are linearly independent, then for design matrix X times parameter vector B equals vector Y, observation vector Y, beta hat equals X transpose X inverse times X transpose times vector Y. Mikhail, that's what I had incorrect on the previous page, right? This beta hat part, right? Okay, so, all right, thank you. So we have that, this is correct. And the thing is, okay. So now go with this corrected version. Thank you. So we want to be able, thank you. We want to be able to use this formula. Okay, and like, for instance, if, let's say that X was equal to foot length. Okay, if X was equal to foot length, okay, and I want to be just careful how I phrase this. And you find two people. One person has a foot that's 12 inches tall, and he's 60. Well, he's 72 inches in height. Okay. Okay. Let's say we're talking about men here. 72 inches in height. And this is your X1. Just kind of keep things separate here. This is your X1 and your Y1. That's a data point. And then we sample a second person, and that person's also has a foot length of 12 inches, and he's 72 inches tall. Okay, that is your X2, Y2. So if your model is Y equals beta naught plus beta 1x, then the design matrix X for this example is going to have a 1, 1 and a 12, 12. A 1, 1 and a 12, 12. What can we say about design matrix X? What can we say about the columns of this design matrix X that corresponds to these two data points. What can we say about the columns of this design matrix X here? Let's see if somebody, let's try to have everybody participate here. Don't be afraid if you say the wrong answer. Nobody's going to make fun of you here. What can you tell me about the columns? The column vectors 1, 1, and 12, 12. Are those column vectors linearly independent or linearly dependent? Dependent. That's right, Bella. So that means that you cannot find your estimates for the parameter vectors using this formula, the beta hat formula. So that's unfortunate, right? But think about the data that we collected. Think about the data we collected. Is the data redundant? Is this data redundant? Person number 1 had a foot size 12 inches long and 72 inches. Person number 2 also. Mikhail says, yes, that's redundant. So you see, you're not really inputting new information in the model when you pick two people that have the same characteristics, so to speak. And this is where linear dependence creeps into the design matrix and causes problems. We don't want to sample, when we take a sample of people and we look at their different characteristics, we don't want to have two people whose characteristics are all the same. That is not informative. Okay, if you have two people in your data set, if you're sampling 30 people, okay, say you spend money to sample 30 people and create a data set. You don't want to have repeats in there. You want to have as much information as possible regarding the population of people. Your sample of 30 people gives you information about the population. And it's very rare that two people will have the exact same characteristics. Okay, so generally when you do your sampling, it's rare. I want to say it's the right way. It would be unusual to have linear dependence among columns in a design matrix, particularly if you're looking at many characteristics. So like if we collected data on foot size and waist size and head size, it increases the number of variables in the problem, the predictor variables, and it helps ensure that you don't have linear dependence in your data set. Okay, so this is a little bit of statistics education I'm giving you here, but you still have to watch for it. And what happens is you can have a data set where you have maybe you have 1,000 people that you sampled and you have all this data on these people. You can actually filter through the data and try to remove dependency if there were two people that had the same characteristics. That would be, you understand what I'm trying to say? Kind of like data mine the data. Does that make sense? I don't want to get too deep in the weeds here, but how many have heard of data mining? the process of finding anomalies, patterns, and correlations with large data sets to predict outcomes. Okay, so I'm just sort of touching the surface here, but now let's go ahead back to the problem. If you want to learn more about this, work on your take some statistics classes, and you will learn a lot of good things. That's for sure. And because my PhD's in statistics, so a lot of beautiful things. It's a great subject to go into. And even if you're in, if you're in engineering, computer science, something like that, you could minor in statistics. But at any rate, okay, so this data, X transpose X, well, the data set X here, let me just, here's your design matrix X. I've highlighted it here. Clearly, those columns are linearly independent, and therefore you can compute your least squares solution for your parameter vectors, and you're going to get those values, 2/7 and 5/14. That's what you're going to get. Now hold on, there was a chat comment here. One moment. Yes, Cameron, absolutely, absolutely. Extremely useful statistics is. Absolutely. And it's so applied in different fields, and it can be applied, and it can, it has a lot of math, a lot of linear algebra, and it's applied, and then there's theoretical math. It's really quite a lovely subject. I'm so glad I went in. So here's your least squares. Here's your least squares line. So 2/7 is the least squares solution for beta 0. 5/14 is the least squares solution for beta 1. And there's your line of best fit. Okay, are there any questions on that? Okay, let's do another problem. I want to do one problem before we go on break here. Yeah, it is really cool. And the thing is, you see, this using the least squares approach with linear algebra allows us to do a variety of least squares problems. I mean, like in some classes, students learn about the least squares line of best fit, but we can adapt this process to a variety of different models. So let me share one with you here. Let's do this example here. Okay, let me give you a moment to copy the example down. Yes, well, Mikhail, what's complicated, of course, is that this is a different model. And this model here, like I know, for instance, how many know, like in their TI calculators, the line of best fit, you can get those coefficients, those least squares coefficient estimates using like the TI calculator. How many of for like regression models? You can actually do that. I don't know if you've been taught that or not, but we need to have with now that we know linear algebra, we can do basically a variety of different models. And in this experiment, we have 3 data points, and we want to find the equation of this form, okay, that best fits the data points. So we need to figure out what our design matrix is, okay, and let me at least do that on this page. What would the dimensions be of the design matrix? How many rows? That's right. 3 rows. That's right, Mikhail, that's right, Cameron. 3 rows and 2 columns. Now, let me ask you this. Don't put this in yet, but would it be okay to have a 1, 1, and 1 here? Is that in our design? So when you had y equals beta 0 plus beta 1x, you can think of that as beta 0 times 1 plus beta 1 times x. Okay. So in that case, okay, let's make that. Yeah, in that case, the 1 here is okay then. Then you have 1s, but you don't have that here. The let me just do this again. So tell you what, let me do this a little differently, because I think, all right, what's the observation vector? What are the y values? Here's the data points. Here's a data point. Here's a data point. Here's a data point. Very good. 7.9, 5.4, and negative 0.9. Okay, that's your y vector. What's your parameter vector here? What are the parameters? In this model, what are your parameters? What are your unknowns? A and B, that's right. A and B. Very good. Very good, Mikhail. And we know that x times the parameter vector, the x times b equals y. Y is a 3 by 1. Beta is a 2 by 1. And so X has to be a 3 by 2. So the question is, what is X? Well, what is the design matrix? The data that you're feeding in, the X values, you're altering them by having the cosine of X and the sine of X. Right? So the data matrix X, the first row would have to be so 3 by 2. The first row would have to be what? Well, we have cosine X and sine of X. So we had cosine of one and sine of one, right? What would the second row be? See that? Good. Good, Mikhail. What would the second row be? All right. Good. Cosine of 2, sine of 2, because here's 2. And the last X value is 3. So you'd have cosine 3 and sine of 3. Okay, so once you have your observation vector, your parameter vector, and your data, your design matrix X, you're good to go. And in the next page, I've rewritten that. So here it is at the top in our solution. And we find the least squares solution using our beta hat formula. And it works because the columns of the design matrix X are linearly independent, meaning that every piece of data that we collected is contributing something new to the understanding of the area we're studying. Now, what you have to do, well, let me give you a moment to copy up to here. Please let me know if you have any questions. Okay, so now X transpose times X, you notice that these like the cosine of 1, let me rephrase that here. You notice that the, cosine of 1, cosine of 2, cosine of 3, I'm not expressing those as decimals. And you have to be careful in MyMathLab not to do that ahead of time. MyMathLab for the design matrix wants the exact values. It does not want decimals. It wants the exact values. So you have to actually get this 2 by 2 matrix here. So you're taking a 2 by 3 and multiplying that matrix by 3 by 2. So that's going to give you a 2 by 2 matrix with those 4 entries. You notice I'm not rounding them. Right, that's correct. That's right, Nikhil. Keep the accuracy, keep the cosine of 1, and then cosine of 2 and cosine of 3, and use the x transpose x, use that for x transpose x, and then take the inverse, and then you'll get your result. But if you round ahead of time, you won't get the right answer. MyMathLab will not accept it. So, and I don't want you to have, you'll probably, you want to do the homework naturally for this 6.6 because it's, going to be on the final exam, right? I would say the new material that you're learning, sections 6.5, 6.6, 7.1, and maybe, well, we'll see, 7.2, that material will constitute a significant part of the final exam. Okay, so you want to make sure you're doing the new homeworks, okay? But yeah, this is what you use. And now, so what I'm saying is in MATLAB, when you type in you're going to use MATLAB to help you with 6.6, but you're going to type this in MATLAB. Okay, actually right, cosine of 1, cosine of 2, cosine of 3. No approximations. Okay. And now, when you compute your beta hat matrix in MATLAB, these are the values you get. And so the least squares model for those points, for the 3 points, is going to be y hat equals 2.3421 times cosine of x plus 7.4475 times the sine of x. Okay, so hold on, I didn't write that right. This is why I don't want you, remember I mentioned at the beginning of the semester not to use hats for vector symbols? That's because hats stand for least squares estimates. And the 2.3421 is your least squares estimate for beta naught, and the 7.4475 is your least squares estimate for beta 1. We denote that by beta 1 hat. See, so you don't want to use vector symbols. They got to stop doing that in like physics classes and stuff. They need to. How many have seen like hats for vector symbols maybe in another class? Some of my students in my other class said they've seen that. Okay, all right. Very good, Mikhail. And so now you have your least squares model. And as always, you can graphically verify that your model is reasonable by plotting the model. And this is where you'd have Cameron. Okay, thank you, Cameron. Cameron does recall it. Very good, very good. You can go into Desmos and plot your coordinates Okay, plot the data points, I'll say. I'll call them the data points. And then plot your curve of best fit over the data points. And notice that the curve starts at a little above 2 because when x is 0, you would just have the first term, right? Cosine of 0 is 1, sine of 0 is 0. So it's going to start at this point. But yeah, you have your 3 data points. Here they are. And it turns out that these data points, the scientists who were trying to model the data were using a model involving cosine of x and sine of x. And it was a good choice because that curve, it doesn't fit the data perfectly, but it's not bad. It's not bad. And there are reasons why you have these different design models for different you know, applications and scenarios. There are reasons for that. So in your homework for section 6.6, you'll have problems that relate to a comet, Kepler's first law with a comet. There's a data model for that. You'll have a problem that relates to radioactive substances. You'll have a different kind of model for that. But all of these models, with the knowledge of linear algebra that you have, you can find least squares solutions for all of them. All right, Cameron's liking this. Good, good. Wonderful, Mikhail. I mean, thank you. How many of you think this is pretty cool? Now, how do you feel about it? You think it's pretty good? Zishan, how about you? Marcella, how about you? You liking it? Okay, very good. Belen? Very good. Belen, how about you? Good. Good. David? Wonderful. Wonderful. Fatima? Okay, find it interesting. That's great. Jacob? I think Jacob, I'm not sure his, I think he's here, but maybe he is, I don't know, maybe his power's low. I don't know, but I know. All right, well, so this is really what section 6.6 is about. And are there any questions at all? I'm really happy you enjoy this. I'm really, really happy about that. All right, Mikhail's good. Notnell's good. Excellent. Okay. Okay. I will go ahead and stop the recording then.